so that you can solve this problem. Okay? And again, I can imagine that this could become one of the exam questions. So first of all, one of the main tricks, and many people make this mistake, is you have to choose your coordinate system right. Of course, a smart student chooses the coordinate system so that it coincides with the long axis of the ellipse and the short axis. Because then your matrix becomes rather simple. 2 of the 4 are 0. There is only stretching and shortening. So choose your coordinate system right. Of course, you can do it in any coordinate system. It will work. But then the matrix will have very complex components. And what is the second assumption that you have to make? The second assumption that you have to make concerns the change in volume or area in this two-dimensional case. In principle, if you say, okay, it used to be circular, you don't know how big the circles were. Maybe the circles were small, maybe they were big. And you can only make a determination or a calculation of the d-tensor if you know the determinant of this matrix, which gives you what the area changes. Okay? So say you assume there has been no area change, then you can make the calculation. It was stretched exactly the same amount as it was shortened in the other direction, and then you can calculate the components. Now this assumption, this zero volume change, is of course not always the case. For example, if you have a sediment, which is a clay, very close to the surface, a clay can have a porosity of 50 or 60%. If you shorten it and bury it to 2 or 3 kilometers depth, the clay has 10% porosity. So there's been a huge amount of water squashed out, exactly like I'm doing now with this sponge. Okay? So a clay which is buried, if it has a circular object in it, it is actually going to become an ellipse, a flattened ellipse, but there you cannot assume that the volume remains the same. Okay? So how do we go about measuring strain in rocks? Well, just like the Mickey Mouse and just like the face, my own face that I've shown you, you need to have something that allows you to know what it used to be. You need to have an object which you can recognize. So of course one thing is fossils. If fossils get buried in the earth, then they will start to deform. Sometimes fossils will start to deform rather heterogeneously. I have a small collection of very rare fossils which deformed in very strange ways. For example, here, this ammonite, it collapsed in the middle. Only the middle part of the ammonite was not strong enough and it collapsed, it became flat, you can see it here, and the outside remained strong and stood up because there was more and more load on it. Okay? Here's another one. This is a sea urchin from the Cretaceous here in Maastricht. It was filled with some kind of a carbonate debris, and then there was more and more overburden load on it, and it just couldn't stand up, and it started breaking in very strange ways. So these fossils could be very nice ways to measure stress, but they certainly are not good to measure strain, because they are very heterogeneously deformed. But there are some other rather interesting objects. A very famous example is in the Hunsrück. It is here quite close to here, around Koblenz, the Hunsrück-Schiefer. They have a beautifully preserved fauna of many, many fossils. And the Hunsrück-Schiefer is a deformed rock. It is quite well developed a cleavage, a schieferung. Okay? And the fossils in this Hunsrück-Schiefer are all deformed. For example, this used to be a circle, this object, and this fossil has been shortened in this direction and stretched in that direction, and of course it changes the shape. Here's another example, and in fact we have these fossils on display here in the glass cabinets. These are trilobites, and we are looking down on the bedding plane. And look here, this trilobite is fat and short, and this trilobite is thin and long. And there are some strange looking trilobites in this direction. In the beginning, paleontologists often made the assumption that these were two different species, until a deformation allowed, basically, or undeformation, to allowed the structural geologists to show that these were all the same trilobites, just stretched and shortened. Okay? And now I think I can ask you, what is more or less the orientation and the shape of the strain ellipse that produced this deformation? Okay? I think what you can say is that it must be more or less parallel to this one, because this trilobite is stretched, but it is not sheared. Okay, so it must be along one of the main axes of the ellipse. So maybe the ellipse is like this. There's shortening in this direction, there's stretching in that direction. And in the tutorial, we are going to teach you how to use deformed fossils to determine the strain. Okay? And the problem is knowing how it looked like and using this information to determine the D. For example, if I have a very nice grid, rectangular lines with a circle in it, and I deform it, it's extremely easy to determine D. You have a lot of information. But if you have a lot of these squashed fossils, then it is not so clear which geometric information you use to actually back out or back calculate your D matrix. There are many tricks for that, and depending on the kind of fossil, you use one of these methods or the other of these methods. And here is just another example of fish. This is actually a fish which I scanned and then put into different orientations, and you can see that you can make fat, short fish and very long, skinny fish and all kinds of strange orientations using just homogeneous deformation, depending on how the fish are oriented. Okay, so in the second half of the lecture, we are going to talk about methods of actually backing out this D using real deformed rocks. But before that, we take a few minutes break. Okay, so now we have learned about the basics of homogeneous deformation in 2 dimensions. We have seen some examples of deformed objects. We have learned that we have to know what the object is before it's deformed, otherwise we cannot really reconstruct. We have learned a little bit about the assumptions. Now let's look at some real work. And the main example that I want to show you is actually made in Aachen. It is one of the very famous contributions to structural geology, the most famous until today by one of the professors who used to be the predecessor of the predecessor of the predecessor of Professor Azam in engineering geology. His name was Hans Predin. I think down here in the engineering geology they have photographs of him, and he analyzed the tectonic deformation of fossils in the mountain belt around us. And he developed a method, the Predin method, and it is actually featured in Ramsey and Huber, the textbook. So please go and have a look at it. What I'm showing you is the actual original pictures from the original Bredin publication. So, we want to understand strain. We want to understand this deformation matrix in rocks. And what we have to work with is rocks like this. Lots of shells which were buried in the earth, and then maybe in the Carboniferous at 10 kilometers depth they were squashed and deformed. And if you learn how to analyze these fossils, then you can back out the strain. Okay? The principle, I've already shown you this ring with the faces. The principle is that if I now give you 4 of these faces, telling you that they all were the same, but oriented differently, before my homogeneous deformation, what information in these faces can I use to calculate my D matrix? And of course, what you can do is you can look at the original symmetry. Remember, the face is symmetric, left side and right side, and here the faces are sheared. Some of the faces are sheared like this, some of the faces are sheared like that, depending on how they are oriented. But what we have here is not the orientation before deformation, we have the orientation after deformation. So we have to know the orientation of the symmetry axis, and we have to know the angle of straining. This is what Bredin came up with. That was his good idea. He found fossils like these two, which used to look exactly the same. But one of them, this one, is now long, and this is short. The reason is that one of them was like this, and the other was like that when the deformation ellipse stretched in this direction and shortened in that direction. So these are the special ones. They are just short and long, but not sheared. And I made you this diagram with the faces. In the original work of Bredin, he made little triangles. It's not so nice as faces, but it works just as well. So these are all the original forms. And if you flatten it and deform it, then one of them will be short, the other will be long, this will be sheared to the left, and this will be sheared to the right. Okay? And maybe you wonder how Bredin actually produced these drawings, because nowadays with a computer it's very easy if you have your drawing program. He produced these deformed drawings by building for his technician a table, a light table with a glass plate, and under the glass plate he had a tilting table. So he had the original drawing and then they twisted it, and the draftsman would draw the deformed shapes. So that is the technique they used. Okay, so here are the different orientations of my shell, and this will be the short one, this will be the sheared, and this will be the long one. And returning to very simple variations of my face, I have now drawn these little crosses for you. And what you see is that for this particular deformation ellipse, this cross is straight, this is straight, and these ones are all sheared that way, but by different angles. You can see that this angle here is different from that one and different from that one. So if I would now go and measure the orientation of these lines, the symmetry axes, together with this shearing angle, then I'm going to get a curve. The orientation changes and the shearing angle goes up and then it goes down, back to 90 degrees.